Hola! Today's adventure takes us to Acuña's Unit 3, Analysis of Deductive Arguments. We will take on an adventure from Modules 2 to 7, which will be discussed by Dora and her amigos. Are you ready? Come on, vámonos! Today's episode is entitled Argument. This is where you will gain knowledge not merely about the fundamentals of assessing a deductive argument, but also the underlying principles for distinguishing between valid and invalid argument forms. But where are Modules 2 to 7? Who do we ask for help when we don't know which way to go? The map! Our destinations for today's adventure are Modules 2 to 7 of Acuña's Unit 3 Analysis of Deductive Arguments. So, tell Dora that you need to go to our first location, Module 2. Where do we go first? Module 2, right? Hola, soy Tico. I will be the one discussing Module 2. This module will provide the basic skill for analyzing and representing compound statements. Let us proceed with a convention for representing statements and logical constants. First is the simple statements. These statements, by definition, contain no connecting words. It can also be represented by using a single capital letter. For example, the bumblebee bat is the smallest mammal in the world. The statement can be represented by any of the 26 letters of the alphabet. It could be represented as B, or it could be any capital letter like Q, R, S, etc. Moreover, it can be noticed how the content disappears when you represent a simple statement with a capital letter. Let us now represent compound statements. These statements contain connecting words that are also called logical constants. What are logical constants? Exacto. Logical constants constitute all the connectives in symbolic logic. And so, we will stipulate the following symbols to represent these logical constants. For conjunction, it has the connecting word and has a symbol like this, a dot. For alternation, it has the connecting word either or and has the symbol like a V. For conditional, it has the connecting word if then and has a symbol like this, an arrow. Lastly, for biconditional, the connecting word used is if and only if, and has a symbol like this, a triple bar. Moving on, suppose we represent the simple statement, Marco is a college student by the capital letter M. Suppose we represent another simple statement, Eliza is a college student by the capital letter A. Now, we are no longer talking about Marco or Eliza, but about their representations. And so, let us now represent different compound statements. Starting with conjunction, to conjoin the two simple statements, we will use the symbol of conjunction. The result is this, and it is read as M and A. The representation of the logical structure of M and A takes the place of the compound statement, Marco is a college student and Eliza is a college student, or the shortened version of the compound, Marco and Eliza are college students. Next is the alternation. Suppose we use alternation and this symbol, the V. The representation of the logical structure is this, and it is read as either M or A or simply M or A. This represents the logical structure of the compound statement, either Marco is a college student or Eliza is a college student. It can also be shortened to either Marco or Eliza is a college student. We can also do the same with the conditional. The representation of the logical structure is this, and it is read as if M, then A, or simply M, then A. This represents the logical structure of the compound statement. If Marco is a college student, then Eliza is a college student. Lastly, let us do the same with the biconditional. The representation of the logical structure is this, and it is read as M if and only if A. This represents the logical structure of the compound statement. Marco is a college student if and only if Eliza is a college student. Now you know how to represent the four compound statements in order to reveal their logical structure. So, let me now introduce the concept of negation. Let us first define negation. This is the action of logical operation of negating or making negative, and it is represented by the tilde symbol. With this, you can negate a simple statement or a compound statement. Let us now negate a simple statement. Suppose the simple statement is, the bumblebee bat is the smallest mammal in the world, and is represented by B. To negate the simple statement B, it could be represented as this. The convention for reading this representation is not B. This represents the negation of simple statement B, the bumblebee bat is not the smallest mammal in the world. Moreover, a compound statement can be negated too. Let us bring back the two simple statements. Marco is a college student represented by M, and Alyssa is a college student represented by A. To negate a conjunction, it is represented like this and it is read as, it is not the case that M and A. To negate an alternation, it is represented as this and it is read as, it is not the case that M or A. To negate a conditional, it is represented like this and it is read as, it is not the case that if M then A. Finally, to negate a biconditional, it is represented as this and it is read as, it is not the case that M if and only if A. In negation, there are rules that you need to take into account. First, if the phrase, it is not the case that, is becoming too redundant, it can be replaced by, it is false that, or it is not true that. Second, if you want to negate the whole compound, we bracket the compound with a parenthesis in order to mark the scope or domain of the negation to avoid confusion. Lastly, you may also negate an element of the compound. To do so, you can remove the parenthesis. For more specific instructions, this is what you can do. In order to negate one element, you remove the parenthesis and put the tilde symbol on the element you're negating, like this. This is read as, if not M, then A. In addition, if you wish to negate both elements, you remove the parenthesis then put the tilde symbol to both elements like this. This is read as, if not M, then not A. Lastly, in order to negate the compound together with its elements, you have to bring back the parenthesis, put the tilde symbol on both elements inside and outside the parenthesis, like this. This is read as, it is false that if not M, then not A. That concludes Module 2. If you understand the discussion, say, argument. Excelente! Where do we go next, Map? Let us now go to Module 3. Hola, soy Isa, and let us now move on to Module 3, Truth Values of Compound Statements. This module will be pursuing the application of the three principles and the analysis of the truth values of compound statements. Let us go on with the first principle, the principle of identity. Suppose we represent the simple statement, earthquake is a sudden and violent shaking of the ground by the capital letter E. And suppose we know that this is true by definition. So, if E is true, then E is true. Alternatively, earthquake is not a sudden and violent shaking of the ground. So if E is false, then E is false. With this, it states that a statement implies itself in this principle. This can be represented as if E then E or if not E then not E. And this statement, in virtue of its form, is always true. Therefore, if E then E is a tautology. This means that truth values are more or less stable over time, guaranteed by this principle. But what is tautology? Exacto. This is a statement that is always true because of its structure, as it requires no assumptions or evidence to determine its truth. Basically, it is a statement that is truth functionally valid, such as universally true or true in every interpretation. Next is the principle of excluded middle. This guarantees that the truth value of any statement like E is either true or false only. This means that the premise and conclusion of a deductive argument can only be either true or false and not both. Thus, it cannot admit the probability of values. The principle can be represented as E or not E. Either earthquake is a sudden and violent shaking of the ground or it is not. You do not have a third truth value. Suppose we know that E is true. Then, without further investigation, you also know that negation not E is false, following the principle of excluded middle. Why? Exacto. because we know that the truth of E is stable over time following the principle of identity, and you know that E can either be true or false only. This relationship is called truth functional relation. This means that E and not E are truth functionally related. But let us try to reverse it. If the affirmative E is false, then it is the negative not E that is true. Note that when you see the negation sign before a statement, it does not necessarily mean the statement is false. A negated statement can be true or it can be false. In short, E or not E is always true because in all possible substitutions of its truth values, the statement is true, thus it is a tautology. Lastly, the principle of non-contradiction. This prevents one from assigning two truth values to a statement at the same time and in the same respect. So, E cannot be both true and false at the same time and in the same respect. Thus, earthquakes cannot be a sudden and violent shaking of the ground and not a sudden and violent shaking of the ground at the same time and in the same respect. This principle is then represented by this, and it is read as, it is not the case that E and not E. Thus, E and not E is always false because a conjunction is true only when both conjuncts are true. Therefore, this is self-contradictory. The denial of a self-contradictory statement of the form, it is not the case that E and not E is always true, hence a tautology. Moving on to negation and double negation. Let us represent the truth value of E and its negation as follows. If E is true, then not E is false, or if not E is true, then E is false. The table reflects the following truth functional relationship. E cannot be both true and false at the same time, for this would be a violation of the principle of non-contradiction. For double negation, if E is denied twice, like in the example, it is false that earthquake is not a sudden and violent shaking of the ground, then it can be represented like this. The convention for reading this double negation is not E or it is not the case that not E. Note that when a statement is denied twice, it implies its affirmation. Therefore, not E is equivalent to E. If, however, E is negated 3 times, this means it is denied. If negated 4 times, it is again affirmed. Now, let us proceed to the truth tables of compound statements. Starting with the truth table of conjunction, let us consider the representation of a junction E and L. To determine the logical form of this compound, let us consult the truth table presented. The first 2 vertical columns of E and L contain all the possible substitution instances of the truth values of the 2 statements E and L. The horizontal shaded in green implies that the conjunction is true only when both conjuncts E and L are both true. In all other combinations of the truth value, the conjunction is false. This means that we are allowed to conjoin 2 or a set of statements provided the statements are true. Thus, it is the only requirement. Note that the premises of a deductive argument, however numerous, are connected by conjunction. This means that if one of the premises turns out to be false, the whole premise set is false. Next is the truth table of alternation. Let us consider the representation of an alternation E or L. To determine the logical form of an alternation, we can examine the truth table presented. An alternation is false only when both alternants are false. In all other combinations of truth values, the alternation is true. This means that the minimum requirement in formulating a true alternation is that at least one of the alternants must be true, regardless if the other is false. Moving on to the truth table of a conditional, let us consider the representation of a conditional if E then L. To determine the logical form of a conditional, let us examine the table presented. The conditional is false only if the antecedent E is true and the consequent L is false. All possible combinations of truth values of the antecedent and the consequent, the conditional is true. With this, we can now discuss the logical form of all deductive arguments. The logical form of deductive arguments is logically isomorphic with the logical form of the conditional statement. Let us compare the previous table with the table of validity for judging whether an argument is valid or not. An argument is invalid only when the premise set is true and the conclusion is false. This corresponds to the only case in which a conditional statement is false, namely, when the antecedent is true and the consequent is false. This means further that the premise set of a deductive argument is joined to its conclusion by the conditional connective. Lastly is the truth table of a biconditional. Let us consider a biconditional E if and only if L. A biconditional is asserting a necessary condition that E is true if L is true, and a sufficient condition that E is true only if L is true. Thus, L is both the necessary and sufficient condition for the truth of E, such that if L is true, you know that E is also true. Or, if L is false, then you know that E cannot be true. A biconditional is true only under two conditions, namely, when both elements E and L are true, or when both E and L are false. In all other combinations, the biconditional is false. A biconditional is defined as E if and only if L, as well as if E then L and L then E. And for the last part of this module, I will discuss the negation of compound statements. The denial of a compound statement with its truth tables are represented as first for conjunction, second for alternation, third for conditional, and lastly for biconditional. It can be observed that when the compound statement is true, then its negation is false, and vice versa. That concludes Module 3. If you understand the discussion, say, argument. Excelente! Where do we go next, Map? Let us now go to Module 4. Hola, soy grumpy old troll. Let us proceed with Module 4, representing arguments. This module introduces the basic rudiments of representing arguments in order to isolate the logical structure of the argument from its content. The first step in representing an argument is to represent the simple and compound statements, like this. The first is the compound statement, the second is the premise, and the third is the conclusion. Let us now represent arguments. Let us consider the following argument. First premise is, if we sleep early, then we increase our energy levels. Second premise is, we sleep early. Conclusion is, therefore, we increase our energy levels. Suppose we represent the premises by using the first letters of sleep and energy, namely, capital letters S and E respectively. And suppose we represent the conclusion indicator, therefore, with the logical convention of 3 dots. The next step is to represent the argument by revealing its logical structure. The vertical representation of the structure of the argument will look like this. As we examine the representation, it can be noticed that they have the same logical structure. The first premise states a conditional, the second premise affirms the antecedent of the conditional, while the conclusion is deduced from the two premises. The logical form of any argument with this logical structure is valid because if we construct the truth table of the argument, it will not have a case where the premise set is true and the conclusion is false. This argument form is called modus ponens. This means that the strength of a deductive argument results solely on the logical form and not on the content of the argument. In contrast, we have invalid argument form. If we argue in the following way, first premise, if we sleep early then we increase our energy levels. Second premise, we increase our energy levels. Conclusion, therefore we sleep early. We represent the structure of the argument in this way. The argument form of any argument with the same logical structure presented, whatever is the content, is invalid. This argument form is technically called the fallacy of affirming the consequent, which is an example of a formal fallacy. The argument affirmed the consequent and not the antecedent, making it invalid. This is because if we construct the truth table of this argument, we will have a case where the premise set is true and the conclusion is false. Let us consider another argument with a different logical structure called addition. Consider the argument. First premise, some people are vegetarians. Second premise, some people are not vegetarians. Conclusion, therefore, some people are vegetarians and some people are not vegetarians. We represent V for the first premise and N for the second premise. The argument structure of the representation of the argument will look like this. Any argument with the logical structure of modus ponens and addition has a logical form that is always valid, whatever its content. Just make sure that both premises are true. With this, we can observe the characteristic of all valid argument forms. The logical structure of various arguments may differ, but if they are valid, they share one common characteristic in their truth tables. Namely, there is no case in which the premise set is true and the conclusion is false. If an argument form has a true premise set and a false conclusion, it is invalid. Moving on, formal deductive logic has another convention for representing structure of an argument. Let us consider this example. We know that the premises of an argument, however numerous, are joined by conjunction. If we apply this to the argument shown, the result is a horizontal representation of the structure of the argument. The premise set are joined by conjunction, and the therefore indicator, the three dots which represent the conclusion indicator, was transformed into the symbol of the conditional. That concludes Module 3. If you understand the discussion, say argument. Excelente! Where do we go next, Map? Let us now go to Module 5. Hola, soy Benny. Let us proceed with Module 5, Basic Deductive Argument Forms. This module will introduce a set of basic deductive argument forms. So, let us now differentiate valid argument structure from those that are invalid by mere inspection. Starting with conjunction, suppose we know that two statements are true. These statements may be any statements unrelated. The only requirement is both statements must be true. So, let us consider a pair of two true statements. The first one is, a mobile phone is an electronic device, while the second one is, a bus is a road vehicle. Let us represent the two statements as M and B respectively. You can conjoin M and B because conjoining two true statements preserves the truth value of the conjunction. This valid argument is technically called a conjunction. The structure of the argument is depicted as first premise is M, the second premise is B, therefore M and B. Now, if conjoining two true statements preserves the truth value of a conjunction, separating their conjuncts preserves the truth values too. Thus, first premise is M and B, conclusion is therefore M, or first premise is M and B, and the conclusion is therefore B. Thus, from a conjunction M and B, you can separate any of the conjuncts either M or B. Consequently, all argument structure like the one presented is valid. This valid argument structure is called simplification. Now, let us discuss alternation. Suppose we know that two statements are true, namely, first is Enhypen is under Belief Lab, represented by capital letter E, and second is Treasure is under YG Entertainment, represented by capital letter T. Then, from the two statements, we can create an alternation, either Enhypen is under Belief Lab or Treasure is under YG Entertainment. With this, the argument structure of alternation is depicted as first premise is E, second premise is T, conclusion is therefore E or T. Moreover, we know that from a conjunction, we can validly infer any of the conjuncts. Unfortunately, from an alternation, we cannot infer any of the alternants, since an alternation is true even if only one of the alternants is true. The invalid argument structure is called subtracting an alternative. The alternants we may infer may be the false one, and we will have a case where the premise set is true and the conclusion is false. With this, the invalid argument structure is depicted as first premise is J or M, conclusion is therefore J, or first premise is J or M, and the conclusion is therefore M. Moving on, suppose you know that the statement Marco lives in Nueva Ecija is true and is represented by the capital letter M. Moreover, you know that the statement Eliza lives in Marikina is false and is represented by the capital letter A. With this, we can still form a valid argument like this. The first premise is M, and the conclusion is therefore M or not A. Hence, this valid argument is called adding an alternative. Next, suppose we know that the statement is true. Unfortunately, we cannot add a conjunct since the statement we might add might be false. So, suppose J is true. Then the first premise is J, and conclusion is therefore J and M is an invalid argument. This is called adding a conjunct. A statement M of undetermined truth value cannot be added to form a conjunction. Let us proceed with an argument called disjunctive syllogism. This is when detaching an alternative is valid since you know that the alternation is true, not because both alternants are true. However, one or the other is false. This has a structure like this. The first premise is J or M, the second premise is not J, the conclusion is therefore M. It also has another variation of the same argument like, the first premise is J or M, the second premise is not M, the conclusion is therefore J. Lastly, there is an invalid argument called denying an alternative. It is invalid because even if you know that the statement is true, you cannot infer that the statement M is false because it can still be true. This argument can then be depicted as, the first premise is J or M, and the second premise is J, the conclusion is therefore not M. Another variation of the same invalid argument is if you know that the statement M is true, you cannot infer that the statement J is false. This could be depicted as, first premise is J or M, second premise is M, and the conclusion is therefore not J. That concludes Module 5. If you understand the discussion, say argument. Excelente! Where do we go next, Map? Let us now go to Module 6. Hola, soy Boots. Let us proceed with Module 6, Complex Argument Forms. This module will provide a technique for discriminating the more complicated argument dealing with conditionals. Starting with the first and second argument forms, modus ponens and affirming the consequent. Depicted on the screen is the valid argument structure of modus ponens. The first premise is if R then L, the second premise is R, the conclusion is therefore L. From the argument structure of modus ponens, you can see that the second premise affirms the antecedent. However, the reverse of modus ponens, called affirming the consequent, is an invalid argument. This is depicted as, the first premise is if R then L, the second premise is L, the conclusion is therefore R. Moving on to the third and fourth argument forms, modus tollens and denying the antecedent. The counterpart of the valid form of modus ponens is called modus tollens. The argument structure is depicted as, the first premise is if R then L, the second premise is not L, the conclusion is therefore not R. The valid form is when you deny the consequent, then you have the valid argument of modus tollens, or you affirm the antecedent and you get the valid argument of modus ponens. If we do the reverse, affirm the consequent or deny the antecedent, we create an invalid argument. Thus, if we deny the antecedent, the first premise is if R then L, the second premise is not R, the conclusion is therefore not L. This argument is invalid and it is called denying the antecedent. Moreover, the fifth argument form is detaching the consequent. It is depicted as, the first premise is if R then L, the conclusion is therefore L. We cannot infer the consequent because the consequent and antecedent of a conjunction can both be false, yet a conjunction can still be true. The sixth argument form is called hypothetical syllogism. This is when the consequent of the first premise is the antecedent of the second premise. The argument structure is depicted as, the first premise is if R then L, the second premise is if L then C, then the conclusion is, therefore, if R then C. The seventh argument form is fallacy of misplaced middle. This occurs when the middle term is undistributed in both premises. Its argument structure is, the first premise is if R then L, the second premise is if C then L, the conclusion is therefore if R then C. The eighth argument form is constructive dilemma. Its logical structure is depicted as, the first premise is R or L, the second premise is if R then D, the third premise is if L then C, the conclusion is therefore D or C. This argument is valid because it affirms the antecedent R and L of both conditionals and therefore, we can validly infer the consequent D or C in the conclusion. Hence, the logical form of constructive dilemma is a combination of two modus ponens. The ninth argument form is destructive dilemma. Its argument structure is shown as, the first premise is not D or not C. The second premise is if R then D. The third premise is if L then C. The conclusion is therefore not R or not L. The argument is valid because it denies a consequent not D and not C of both conditionals and therefore, we can validly infer the denial of the antecedent in the conclusion. Hence, the argument structure of destructive dilemma is a combination of two modus tollens. The last two argument forms are two fallacious forms of dilemmas that might appear valid but, on closer inspection, are not. They are called pseudo-dilemma. Pseudo-dilemma 1 denies the antecedent and pseudo-dilemma 2 affirms the consequent. Let us take up pseudo-dilemma 1 first, whose argument structure is: the first premise is if R then D, the second premise is if L then C, the third premise is not R or not L, the conclusion is therefore not D or not C. This fallacy denies the antecedent of the first and second premises, and so we cannot conclude the denial of both consequents. Lastly, another invalid argument form, often confused with the valid one, is pseudo-dilemma 2. Its structure is depicted as: the first premise is D or C, the second premise is if R then D, the third premise is if L then C, the conclusion is therefore R or L. This invalid argument does the opposite. It affirms the consequent of the second and third premises, and so it cannot affirm the antecedent. That concludes Module 6. If you understand the discussion, say argument. Excelente! Where do we go next, Map? Let us now go to Module 7. Hola, soy Dora. Let us proceed with Module 7, Truth Table Method. This module will teach you how to apply the truth table method in determining the validity or invalidity of any argument form. Let us begin from what is familiar. We know by mere inspection of the logical structure of the argument called modus ponens that it has a valid argument form. Its logical structure is depicted as: the first premise is if S then E, the second premise is S, the conclusion is therefore E. Strictly speaking, the argument form or logical form of an argument refers to its truth table and not to its argument structure. Let us proceed to the steps that we have to follow in order to use the truth table method efficiently. The first step is we have to represent the argument in horizontal form like this. The next step is to count the number of simple statements in the argument. Notice that we have 2, S and E. You can use this formula. 2 raised to n is equal to m, where n is the number of simple statements you have and the m is the number of rows created. Now, we have to construct a table for all the possible substitution instances of the truth values of S and E. The table shown will illustrate this. Finally, after completing our table of substitution instances, we have to assign the truth values to the statements in the argument structure. Notice how the table facilitated the assignment of truth values to the structure. It can be observed that there is no horizontal in which the premise set is true and the conclusion is false. Consequently, in all possible substitution instances of the truth value of the statements of argument, the argument form is valid. Thus, it is a tautology. But now, let us consider the invalid form of affirming the consequent. Its logical structure is depicted as: the first premise is if S then E, the second premise is E, the conclusion is therefore S. With this, let us apply the steps mentioned a while ago. The first step is to represent the logical structure of the argument in horizontal form like this. Then, we construct a table of substitution instances. Lastly, we assign the truth values to the argument. Notice that in this argument form, we have a specific case where the premise set is true and the conclusion is false. This makes the argument form invalid. It must be noted that an argument form refers to all the possible combinations of a specific case like the table shown. An argument form is valid if and only if there is no specific case where the premise set is true and the conclusion is false. Just in case the argument form has a specific argument where the premise set is true and the conclusion is false, then the argument form is invalid. Consequently, the term valid or invalid should be used to the argument form only, not to a specific argument, especially in symbolic logic. Moreover, there is a shortcut method of using the truth table in order to determine whether an argument form is valid or invalid. This method is commonly needed when dealing with argument forms with 3 or more statements, which is called the falsification method. This method capitalizes on this by simply attempting to falsify the conclusion while demonstrating that the premise set is true. Let us consider this argument. If P are Q and Q are R, then P are R. First, the intention is to falsify the conclusion while retaining the truth of the premise set like this. We then begin our analysis from the conclusion. If P or R is false, this means that both P and R are also false. If the premise set is true, this means that both alternation, P or Q and Q or R, are true. If P and R are false, the same values should be assigned to P and R in the same premise set. Thus, we are left with only Q. Notice that whatever the value of Q, either true or false, we have discovered a row where the premise set is true and the conclusion is false. The argument form, therefore, is invalid. Let us consider another argument. If R then L, and if L then C, then R and C. Let us apply what we did a while ago to the first argument. Let us first falsify the conclusion while retaining the truth of the premise set. If R then C is false, this means that R is true and C is false. And if the premise set is true, then both conditionals are also true. It can be observed that whatever value we assign to L, we cannot retain the truth of the premise set while maintaining the falsehood of the conclusion. The argument form is therefore valid. If L is true, the second conditional will be false but the conjunction of the premise set will be false. However, if L is false, then it is the first conditional that will be false and the conjunction of the premise set will also be false. A word of caution is appropriate here. When we have discovered a horizontal in which the premise set is true and the conclusion is false, we have a conclusive evidence that the argument form is invalid. However, if we do not succeed in several attempts in falsifying an argument, it does not necessarily mean it is valid. There are cases where a false conclusion offers other possible combinations of truth values. In such a case, we must go about eliminating possible falsifying rows in a systematic way. The following example will serve to illustrate this. If R then L and L then C, then R and C. We know that the first step is to falsify the conclusion while retaining the truth of the premise set. Notice that if the conclusion is false, there are three possible combinations of truth values. Let us now assign the truth values of R and C in the first row. The next step is to assign the possible truth values for L like this. It can be observed that the truth values in the box cannot be true, and therefore, we cannot maintain the truth of the premise set while retaining the falsity of the conclusion. It seems that the argument could not be falsified, and we might jump into the conclusion that the argument form is valid. But remember, there are other combinations of truth values in the conclusion considering that it is a conjunction. Notice that in the remaining combination of the truth values of R and C, we were able to falsify the conclusion while retaining the truth of the premise set. The argument form, therefore, is invalid. Remember, only one example of a horizontal where the premise set is true and the conclusion false is sufficient to judge an argument form to be invalid. But not being able to succeed in doing so does not necessarily mean that the argument form is valid until we have exhausted all the possibilities. These possibilities are dictated by the possible distribution of the truth values of a false conclusion. If the conclusion is a single statement, it has only one possibility. If the conclusion is a disjunction or a conditional, then there is only one possible combination of truth values to make it false. However, if the conclusion is a conjunction, it has three combinations, and if it is a biconditional, it has two. If you understand the discussion, say, argument. Excelente! Wow! We just finished Acuña's Unit 3 Modules 2 to 7. We had such an exciting trip today. We couldn't have done it without you. Gracias!